Today we're going to talk about acid-base reactions and buffers. Okay, so let's start by talking about strong acid and strong base reactions. When you have a strong acid reacting with a strong base, it's essentially a double replacement reaction. And so you're going to form some kind of salt and water. So that's why sometimes this is called a neutralization reaction, because you're forming water. But it doesn't always end up in a neutral solution. It depends on how much of the acid and how much of the base you use. Now typically, you're going to be asked to write a net ionic equation for this. So because the strong acids and strong bases are completely soluble, all of the ions here split apart. And on the product side, KCl is a soluble salt, so you would split that. That's completely soluble as well, and then the water stays together. So your net ionic equation would be the hydrogen plus hydroxide yields water. And so that is going to be essentially your net ionic equation for all of the strong acid, strong base reactions. Now, when we have problems surrounding strong acid, strong base reactions, we're going to use a strategy, and I'm going to introduce what we call the BCA chart. Okay, it's essentially an ice chart, but ice charts you can only use molarity or ATM. BCA chart, it must be in moles. Absolutely must be in moles. So that's how I can differentiate between the two. So what you would do, BCA, is so the water doesn't matter, but you would figure out how many moles of your acid you have before the reaction, and that would go here, and how many moles of base you have before the reaction, and that would go here. Now if you have a polyprotic acid like H2SO4, make sure you're paying attention to how many hydrogens, how many moles of the hydrogen ions, and how many moles, if you have like calcium hydroxide or something where there's 2 hydroxide ions. Again, pay attention to how many moles of the hydroxide you have. So you calculate the moles of each. And then whichever one is smaller gets completely used up. So if they were exactly equal, right? So let's let me make up some numbers. Let's say we have 4 moles of the acid, of the hydrogens and 4 moles of the hydroxides. Then they're exactly equal. They would both decrease by 4, and you'd wind up with none of those and only water. And so the pH would be neutral. Okay, but if you have, say, let's have 4 moles of the hydrogen ions and 2 moles of the hydroxide, well, then the hydroxide will get completely used up. But since it's a 1-to-1 relationship, they're both going to go down by 2 moles. And you wind up with 2 moles of the hydrogen ions left over and none of the hydroxide. When this happens, when you have an excess number of moles of either one, you're going to then take that moles and divide by the total volume. And this is probably the biggest mistake people make. They forget to add the 2 volumes together. And then once you get that, you'll have the molarity of the hydrogen ions. Well, you can just take the negative log of the molarity of the hydrogen ions, and you'll get the pH. So let's do real quick what it would be in the reverse. Let's say we have more of the strong base. Let's say I have 6 moles of hydroxide. Okay, I'm going to completely use up the hydrogen, but since it's 1-to-1, I can only use up 4 moles of each of those. And so I'd have no hydrogen ions and 2 moles of the hydroxide ions. Well, then you would do 2 moles over the total volume, and that will give you the molarity of the hydroxides. If you take the negative log of that number, you'll get the pOH, and you can subtract from 14 to find the pH. So that's your strategy for solving with strong acids and strong bases. Now, when you have a weak acid with a strong base, let's use like HF with sodium hydroxide. Okay, this is a weak acid and a strong base. It's still going to react in the same pattern. You're still going to form some kind of salt, and you will form water. So you still form water and some kind of salt. The salt may or may not be soluble depending on your ions. Most likely it will be soluble because a lot of the group 1 metals are part of your strong bases, but it doesn't have to be. So when you're writing your net ionic equation, then whichever one is the weak one, you want to leave that together on the reactant side. And then strong acids and bases completely break up into ions. And sodium fluoride is soluble, so we're going to split that apart. And the water stays together. And so sodium is our spectator ion, so we wind up with HF reacting with hydroxide to form F negative plus water. Okay, and so those are states. This reaction then, this would be our acid, our base, our conjugate base, conjugate acid. Okay, but you can still solve problems with weak acid, strong base reactions using a BCA chart. Okay, and remember BCA is for moles. And the same thing will happen if you have equal moles of each. You'll wind up with only F negative. Let me just do some examples. So if we have a BCA, okay, the water doesn't matter because it's a liquid. All right. The first step would be to calculate the moles of your acid and your base, and you're not going to have any of the F negative to begin with because we're assuming like this is before the reaction happens. So let's say I have 2 moles of the acid and 2 moles of the hydroxide. Since it's the same, they will both get used up completely, and this will increase by the same amount according to your stoichiometry there. So you'd wind up with 0 moles of the weak acid, 0 moles of hydroxide ion, and 2 moles of your F negative. Once you get there, you're going to divide by the total volume. It's a really important step to remember. And that will give you the molarity of your conjugate base, whatever it happens to be. Well, conjugate bases of weak acids will have Kb values. And so that's important. If HF has a Ka value, F negative will have a Kb value. And then you're going to use that Kb value into the molarity of the fluoride to solve for the pH of the solution following the same steps that we took in section 8.3. So that's your strategy there. So if you have equal moles of both things, you're going to end up with just the conjugate base. You'll use a Kb for the conjugate base following the steps from section 8.3. All right, let's look at another scenario. If I have, let's say I have more of the base, okay, more of the base. Then I'm going to completely use up my weak acid, and I'm going to use up some of that hydroxide, and I'll have 2 moles of hydroxide excess. This will increase by 2. I'll have 2 moles of the F negative. So hydroxide ions, that's your base in this reaction. Fluoride ions are your conjugate base. This one is going to have much, much greater effect on your pH than the conjugate base here. The conjugate base is going to be pretty weak. So what we can do is kind of ignore this and just use that 2 moles of excess hydroxide and divide by the total volume. And use that for our molarity of the hydroxide. Take the negative log of that value, and you'll get the POH of the solution. Subtract from 14 to get the pH. So if you have more of your strong base, you can ignore the conjugate base and just use the excess moles of strong base to figure out the pH of the solution. All right, now the last scenario then would be if you have excess weak acid. I'm going to show you how the BCA chart works for this. So let's choose this. I have excess weak acid. I'm going to completely use up the strong base. So this can only go down by 4. This one will increase by 4 moles. This will be 2 moles. For both of these, you would divide by the total volume. And then we're going to use something called the Henderson-Hasselbalch equation. Now, we're going to deal with this. This makes what we call a buffer solution because it has a weak acid and its conjugate base. We're going to deal with buffer solutions later on. So for now, we're just going to leave this. Just know that this is another scenario, and we will get to how we solve this later. Okay, so our next scenario is a weak base and a strong acid reaction. Let's use ammonia as a weak base and a strong acid. Let's use HBr. And so when they react, they form ammonium and bromide. Okay. If we were to write a net ionic equation for this, the NH3 is our weak base. The HBr splits apart into hydrogen ions and bromide ions because it's a strong acid. And then we have those bromide ions sitting around. So the bromide becomes our spectator ion. And we wind up with an overall equation of ammonia plus hydrogen ions yields ammonium ions. And so this is our base, and this is our acid, and this is our conjugate acid. The bromide is the conjugate base, but it's not in our overall. Now, it works almost exactly like a weak acid-strong base reaction, so I'm going to go through the BCA chart very quickly. You always assume that before the reaction we don't have any of the product because it hasn't reacted yet. If they're equal, let's say I have 2 moles of each, they will both get used up completely, and this will increase by 2. So then you'll have 2 moles of the ammonium at the end of that reaction there. What you'll do is take that 2 moles of ammonium, divide by the total volume, and that will give you your molarity of the ammonium. And ammonium, as your conjugate acid, it will have a Ka value. You can use that Ka value and the molarity to solve for the pH of the solution, just like we did in section 8.3. So that's your first scenario when they're equal. Your second scenario would be if you have excess strong acid. So let's say I have 4 moles of our strong acid and 2 moles of our weak base. We're going to completely use up the weak base, and this will increase by 2. You'll wind up with 2 moles of excess acid and 2 moles of our conjugate acid. So this one's going to much greater have an effect on the pH of the solution as compared with the NH4. Therefore, we can kind of ignore the NH4 and just use the 2 moles of hydrogen ions divided by the total volume, and you'll get the molarity of the hydrogen ions. All you have to do is take the negative log of that value, and you'll get the pH. So we like that scenario. When the only other scenario you could possibly have would be is if you have excess weak base like this. If I have excess weak base, then I will completely use up the hydrogen ions. And I will wind up with the ammonia and the ammonium, so the weak base and the conjugate acid, both of those at the end of this reaction. That forms what we call a buffer solution, and we will talk about how we solve that in a later section. Now, the last type of reaction is a weak acid with a weak base. You need to be able to write the reactions, but you won't necessarily have to do any calculations with that. So if I have a weak base with a weak acid, they're going to form, it's going to just transfer the protons. So we've got NH4 plus F negative, base, acid, conjugate base. This reaction, since they're both weak, it will form an equilibrium system, and in theory you could have a K value for that equilibrium system, but I've never seen any questions that ask you to do anything with that K value for weak acids with weak bases. Typically they will give you reactions where one of the things is weak and one of the things is strong, or where both of them are strong. So let's look at an example of this one. I have 100 milliliters of 0.1 molar acetic acid, so CH3COOH. Remember, this last hydrogen is the acidic one. Potassium hydroxide. And so our reaction will form, I'm going to go ahead and skip to the net ionic equation because I know that potassium is going to be a spectator ion. So it's going to form water and the CH3COO minus, okay, conjugate base. Calculate the pH of the resulting solution, and then they give you the Ka. So I'm going to use a BCA chart because it's a reaction and the water doesn't affect our answer. I don't have any of the conjugate base to begin with, but I need to calculate the moles of each. So that's 0.1 liters times 0.1 molar, that's 0.01 moles. 0.1 liters, 0.1 molar, that's 0.01 moles. Okay, so I have 0.01 moles of each. They're equal moles, right? So that means that both of them will get completely used up because they're equal. And so the conjugate base will increase by 0.01 as well. So I have 0.01 moles of that conjugate base. From here, I need to use that conjugate base to find the pH of the solution because it's the only thing left. What I can do is I can use the equation Kw equals Ka times Kb. And Kw is 1 times 10 to the negative 14 equals, our Ka is 1.8 times 10 to the negative 5 times Kb, and you can solve for Kb. So Kb for the CH3COO negative is 5.6 when you divide that times 10 to the negative 10th. Okay. You also need to, let's go ahead and write our reaction for the CH3COO minus in water, because that's all that's left, right? A fraction of that will form acetic acid, and you'll leave behind some hydroxide ions. So my Kb expression is the acetic acid times the hydroxide ions all over the CH3COO minus. And so now I'm going to start plugging in those values. I have, and again, this is following the pattern from section 8.3. I have my 5.6 times 10 to the negative 10th, and it will be x squared over the I forgot to calculate the molarity. So this is the 0.01. You have to divide by the total volume. We added 100 milliliters and 100 milliliters, so that's 0.2 liters total will give me my molarity of my conjugate base there, which is 0.05 molar, and that minus x at equilibrium. Now I can go ahead and solve for x, which is 5.3 times 10 to the negative 6. When you take the negative log of that, you get the pOH is 5.28. Subtract from 14, you get the pH. If you're confused about this part, please go back to section 8.3 and watch that video again. Okay, here's another example. What is the pH of a solution when we have sodium hydroxide, NaOH, and hydrochloric acid? So they're both strong. That's nice. Well, we know that when we have a strong base with a strong acid, they're going to form a net ionic equation that looks like this. And so for my BCA chart, because it's a reaction here, I don't need to include water, that's a liquid, but I need to go ahead and calculate my moles to begin with. For the base of the 0.5 liters times 0.25 molar is 0.125 moles And for the acid, the 0.4 liters times 0.2 molars, 0.08 moles. So whichever one's smaller gets completely used up. So the acid gets completely used up. And let me subtract to find the moles of base in excess. I have 0.045 moles of base in excess. So the 0.045 moles, I'm going to divide that by the total volume, which is 900 milliliters or 0.9 liters. And I get 0.05 molar hydroxide ions. And that's how much excess base I have. From there, I can just take the negative log of this to find the pOH, which is 1.301, and then subtract from 14 to find the pH, 12.699.